For part A over here, what we want to first do is to rationalize z. So I'm going to multiply the numerator and the denominator by the conjugate of the denominator, which is 1 plus lambda I. So I'll multiply this in the numerator and the denominator. So for the denominator, we will be obtaining a 1 square plus lambda square. As for the numerator, let's expand this. So lambda times this gives me lambda, then plus this times this gives me lambda square I. This minus 4i, and this times this gives me minus 4 lambda I square, which will be plus 4 lambda. And I'm going to regroup the numerator so that the real parts are together and the imaginary parts are together. So lambda and 4 lambda gives me 5 lambda. And as for the imaginary parts, it is going to be lambda squared minus 4. So this is going to be divided by 1 plus lambda squared, which is a real number. So I can now break up this into two parts, which is 5 lambda over 1 plus lambda squared, and I of lambda squared minus 4 divided by 1 plus lambda squared. So now what we have is z being re-expressed into the real portion. So this is the real part of z, and this is the imaginary portion of z. And according to what the question says, the argument of z is equal to pi, which means that if we were to try sketch a point that is on the Argand diagram to represent z, z is going to be somewhere represented by a point that is here, because a point that is here has an argument that is pi. Okay, which means that what we will be expecting for z is that it is going to be a negative real number, which also implies that the imaginary part of z has to be equal to 0. So I'm going to write something that is like this. Since the argument of z is given to us as pi, this tells me that the imaginary part of z, this must be equal to 0. So the imaginary part of z, let me quote it here, lambda square minus 4 divided by 1 plus lambda square. This must be equal to 0, which means that lambda square minus 4 must be equal to 0. This tells me that lambda is equal to plus or minus 2. We're going to make use of these two values, these two possible values for lambda, to find the value of z. Let's check. So when z is equal to minus 2, when lambda is equal to minus 2. So when lambda is equal to minus 2, let's find out what is z. Z is equal to 5 times of minus 2 divided by 1 plus minus 2 square plus I of, this must be 0, right? Because that was how we started off when we want to get the value for lambda. The imaginary part of z is equal to 0. And this, we are going to be getting a minus 2. And this is okay, because we are expecting z to be a negative real number. What if lambda is equal to 2? Then z will be 5 times 2 divided by 1 plus 2 square plus I of 0 once again. And this, we are going to be getting a positive 2, and this is not going to be the value of z that we're going to be considering. So this is not applicable, and the reason is because the argument of z has to be equal to pi. So we have only one single value for z, and that is minus 2. To re-express z into the polar form, let's first try to re-express the numerator 1 plus I into its polar form. So the modulus of this is going to be square root of 1 square plus 1 square, which is going to be square root of 2. Let's try to find the argument of 1 plus I. If I were to sketch a representation of 1 plus I on an Argand diagram, it is going to be represented by a point here, 1, 1. So here is 1, here is 1. This is going to be the argument, which means that the argument of 1 plus I, this is equal to tangent inverse of 1 over 1, which is pi over 4. So we know that for the numerator, it is going to be re-expressed as square root of 2e to the power of I of pi over 4. We will do the same thing for the denominator. And if you were to look at it, the denominator is actually the conjugate of the numerator. So the conjugate will share the same modulus as its original complex number, which is going to be square root of 2, and its argument is going to be negative of the original, so negative of pi over 4. So this is going to be square root of 2 divided by square root of 2 is 1, then e to the power of I of, using indices, pi over 4 minus pi over 4. So z is going to be e to the power of I of pi over 2. As for w, this is going to be square root 2. This, we have already found it. It is going to be square root 2 e to the power of I of pi over 4. So this divided by this is going to be 1 over e to the power of I of pi over 4. Applying indices, bringing this to the numerator, we will be getting this as e to the power of minus I of pi over 4. Here we are going to try sketch points A, B, C, where point A represents the complex number z. And for the complex number z, its modulus is 1, and its argument is pi over 2, which means that z is going to be represented by a point that is somewhere here, where it is of a distance of 1 from the origin, and its argument is pi over 2. We can see it over here because point A lies on the imaginary axis. As for point B, it represents W. So its argument is going to be minus pi over 4. So minus 45 degree. Its modulus is 1. So it's going to be the same distance as OA. So let me draw a reference line from here down with a distance that is approximately the same as this. So let's say B is here. So this is B, and this angle here will be minus pi over 4. The distance is going to be the same distance as this. So let me mark down this. Okay, so we have this. And this point A here has a coordinate of 0, 1. As for point C is representing Z plus W. So we have one complex number plus another complex number. And like what I have discussed in the topical outline on Achevas TV, we are supposed to see this as if it is 2D vectors addition. So it is like vector Z plus vector W. So we're going to apply the parallelogram law. So I'm going to draw a line that is parallel to OB from A. So let's say it is somewhere here. And I'm going to draw a vertical line which is going to be parallel to OA. So this will give me a parallelogram. And connecting the diagonals together, the end of the diagonal here is going to be point C, which will represent Z plus W. And we are supposed to state the shape of this quadrilateral OACB. We know that it is a parallelogram. And at the same time, since OA is the same length as OB, so this parallelogram is also a rhombus. So I'm going to state it here. So OACB, this quadrilateral, is a rhombus. The first thing that we want to do in part 3 is to locate pi over 8. So we can work with different angles that we can see in part 2. And in the end, you will actually end up with one particular angle that is going to be pi over 8, and that is this angle. So let's say we have already done our trial and error. We want to find this angle, and I'm going to name this part here D. So this point here, I'm going to call it D. And let's try to find angle COD. So for this angle COD, my plan is this, is to find angle COB minus away angle BOD. So angle COB. Okay, this angle here minus away this angle BOD, which I already know it is going to be pi over 4. For angle COB, for this angle, it is half of angle AOB. So it's going to be half of this angle AOB, which is very easily calculated because we know that this angle here is 90 degrees. This angle here is 45 degrees. So it is pi over 2 plus pi over 4. So this minus away pi over 4. And this gives me pi over 8. So we are supposed to find the tangent of pi over 8, which is tangent of this angle. So it is going to be opposite over the adjacent. Opposite is CD, which is the y coordinates of point C, and the adjacent is OD, which is the x coordinate of point C. And C represents the complex number z plus w. So let's try to find z plus w in the Cartesian form, because that will give me the x and y coordinates of point C. So z, which we found in part 1, it was e to the power of I pi over 2 plus I w, plus w is e to the power of minus I pi over 4. So re-expressing this back into the Cartesian form, this will be cosine pi over 2 plus I sine pi over 2 plus this is going to be cosine of minus pi over 4 plus I sine of minus pi over 4. Cosine pi over 2 is 0. Then sine pi over 2 is 1. So this we have I. Plus cosine minus pi over 4 is 1 over square root of 2. Sine minus pi over 4 is minus 1 over square root of 2. So minus I 1 over square root of 2, which now I know I can re-express this as 1 over square root of 2 plus I of 1 minus 1 over square root of 2. So we know that for the point C, the x coordinate is 1 over square root of 2. The y coordinate is 1 minus 1 over square root of 2. And like what we have just mentioned, CD here, which is the y coordinate, will be 1 minus 1 over square root of 2. The x coordinate, which is OD, the x coordinate is 1 over square root of 2. And this makes it possible for me to now find tangent of pi over 8. It is just going to be opposite over the adjacent. So 1 over square root of 2 divided by 1 over square root of 2, which is 1 minus 1 over square root of 2, multiplied by square root of 2. And this gives me a square root of 2 minus 1, which is what the question wants me to show.